Welcome you all to chemistry. In this problem solving session, we will try to cover concept based problems of hydrocarbons. As all of you know, hydrocarbons can be divided into two groups, aliphatic and aromatic hydrocarbons. Aliphatic hydrocarbons can be further divided into saturated and unsaturated hydrocarbons. Saturated hydrocarbons refer alkanes. Unsaturated hydrocarbons can be further divided into alkenes and alkynes. Now let us look at the problems. The first one involves hydrogenation of compound A having molecular formula C7H14 produces a chiral compound B with molecular formula C7H16. Reaction of compound A with ozone followed by dimethyl sulfide or zinc in water produces compound C and D. Compound C shows a positive haloform and tolerant test. Identify A, B, C and D. From the molecular formula of A, we can predict it is an alkene as it fits with common formula CnH2n. Compound C shows a positive haloform and tolerant test. It means it has a methyl group which is bonded with a carbonyl group. When you have the methyl group which is bonded to a carbonyl group, it can show a positive haloform test. And it also shows a positive tolerant test. That means it is an aldehyde. The structure of compound C is acetaldehyde. Once, if you know the structure of C, we can try to predict the structure of A, this alkene. So when you do the hydrogenation, it can convert into this alkane. If you look at here, this carbon is bonded with 4 different groups. It is a chiral compound. The structure of compound B is this one. From this now we can predict the structure of compound D. So tolerance test, all of you should know, it is a silver complex. when we use 2 equivalent of this silver complex with aldehyde, it can oxidize to carboxylic acid where silver 1 will be reduced to silver 0. This is often used to find out the presence of aldehyde group in the molecule. And when you have the methyl group which is bonded to the carbonyl group, and it can be oxidized to carboxylic acid and haloform when you react with sodium hypohalite. So these are the tests commonly used to find out the presence of methyl group as well as the aldehyde functional group. So in this reaction, the alkene, when we do the hydrogenation, it gives a compound B. As you can see here, it is a chiral compound. The carbon is bonded with 4 different groups. Ozonolysis already we have discussed, and in this alkene undergoes 1,3 cycle addition reaction to give the cyclic intermediate, which rearranges to ozonide. So this ozonide, when you react with dimethyl sulfide, for example, you will be able to form the carbonyl compound plus this can convert into carbonyl compound and dimethyl sulfoxide. Now let us move to the next problem, which involves the reaction of compound A having molecular formula C8H6 with hydroboration and oxidation yields compound F having molecular formula C8H8O that shows a positive Fillings test, while the reaction of compound E with water in the presence of acid gives G, which shows a positive haloform test. Identify E, F and G. The compound F having molecular formula C8H8O shows positive Fillings test. That means it is an aldehyde. Compound G, which shows a haloform test, that means it has a methyl group which is bonded with a carbonyl group. From this, we can try to predict the structure of E. Hydroboration oxidation, it can be carried out. If you have the phenylacetyl, when you do the hydroboration using borane like hexyl borane, which can undergo addition reaction, let me write or this portion as once if we have this one, you can oxidize using hydrogen peroxide in the presence of sodium hydroxide. to give enol, which will convert into aldehyde. The structure of compound F is this one, which is called as phenylacetaldehyde. If you have the phenylacetylene, which can undergo hydroboration to give this intermediate, this can be oxidized to enol. That enol can be converted into aldehyde. Filling solution is a mixture of copper sulfate and sodium potassium salts of tartaric acid. It's a copper 2 complex. When you mix with aldehyde, it can oxidize to carboxylic acid, where copper 2 will be reduced into copper 1 oxide, which will precipitate as red brown precipitate. This test is often used to find out the presence of aldehyde functional group in the molecule. While the reaction of E with water in the presence of acid gives compound G, this can convert into acetophenone. You can see here compound G shows a positive haloform test. That means it has a methyl group which is bonded to the carbonyl group. When you treat this compound with the sodium hypohalite, it can oxidize into benzoic acid and haloform. The structure of compound E is now phenylacetylene. If it is phenylacetylene, it can be reacted with borane to give this intermediate that can be oxidized to this enol. This will convert into aldehyde, which can show the positive Fillings test. On the other hand, phenylacetylene can undergo addition with water, hydration, the presence of acid to give this enol. This will convert into ketone. This ketone can be converted into carboxylic acid and haloform by reacting with sodium hypohalite, and the structure of compound G is shown here. This is acetophenone. Now let us move to the next problem. Complete the following reaction sequences. The first example involves alkylation of aromatic system. This can be carried out if we have propene in the presence of acid it can undergo protonation to give isopropyl cation, which can undergo reaction with this benzene via aromatic electrophilic substitution to give the isopropyl benzene. Alternatively, if you have the isopropyl chloride, you can react with aluminum chloride to produce isopropyl cation, which can react with benzene ring via aromatic electrophilic substitution to give this cumene. Once if you have this one, this can be converted into phenol by its two-step process. First, we have to react with oxygen to form a hydroperoxide. Once you form the hydroperoxide, when you treat with acid, it can give phenol. When you react cumene with oxygen, the benzylic CH bond undergoes oxidation to give cumyl hydroperoxide. Once you form the cumyl hydroperoxide, when you treat with acid, it can protonate this OH group to give this intermediate. Now the phenyl ring can undergo rearrangement. To give this intermediate, which can react with water can convert into phenol and acetone. It is an industrial process. This we use to prepare phenol. So it depends upon the alkyl group. In this case, if you use this propene, the presence of acid, you can protonate to form the isopropyl cation, which can act as electrophile. Now it can undergo aromatic electrophilic substitution to give this cumene. Once you form this one, the benzylic CH bond can undergo oxidation with the oxygen to form the hydroperoxide. Hydroperoxide, the presence of acid can undergo protonation to give this intermediate. When can the phenyl ring can undergo rearrangement to give this intermediate. This can undergo reaction with water to form this, and which can convert into phenol and acetone as the product. Alternatively, if we have the isopropyl chloride, we can also try to react with Lewis acid like aluminum chloride. and you will be able to form the isopropyl cation and aluminum tetrachloride, which can act as electrophile, which can undergo reaction with benzene ring to give the cumene, which can be further reacted as we have seen earlier to give phenol and acetone as the product. This is known as Friedel-Crafts alkylation. The next example involves acylation of aromatic ring. Here the benzene is converted into acetophenone. This can be accomplished if you have the acetyl chloride, which can be reacted with anhydrous aluminum chloride, to give this carbocation and aluminum tetrachloride. This can act as electrophile, which can undergo acylation with this aromatic ring, as just we have seen, and you will be able to get this acetophenone as the product. On the other hand, you can also use acetic anhydride This also can undergo reaction with aluminum chloride to give the acylium carbocation, which can undergo reaction with aromatic ring to give acetophenone as the product. This can be oxidized to benzoic acid, just we have seen earlier. When you react with sodium hypohalite, you can oxidize into benzoic acid and haloform. These are the important reactions. The first example involves Friedel-Crafts alkylation. If you have alkyl halide, in the presence of Lewis acid can be reacted with the aromatic system to give the alkyl benzene, which can be further converted into useful compounds. The next example involves acylation. This is known as Friedel-Crafts acylation. If you have the acid chloride, you can try to react with aluminum chloride to form the acylium carbocation, which can act as electrophile, which can undergo aromatic electrophilic substitution reaction with, in this case, this acetophenone can be further oxidized to benzoic acid using sodium hypohalite. Here the reaction of nitrobenzene with a mixture of nitric acid in the presence of sulfuric acid is shown, is a nitration reaction. When you take a mixture of nitric acid and sulfuric acid, you will be able to form anode plus, which is electrophile, which can undergo reaction with this aromatic system. And here you look at, already you have the substituent. Now in this case, the nitration will take place in this position. You will get this 1,3 dinitrobenzene as the product. This compound, when you react with sodium sulfide, it can selectively reduce one of the nitro group without affecting the other one to give this compound. Sodium sulfide is known to selectively reduce NO2. If you have the dinitrobenzene, it can, one of the nitro group will be reduced into amino group, the other one will be intact. Now, the position of this nitration is crucial here. The nitration takes place at the meta position. This is because if you try to write the resonance structure, you will be able to understand. If the reaction takes place in the meta position, and you will be able to form the following resonance structures. You have the electron withdrawing group, and if the nitration takes place this position, you will be able to have this following resonance structure. Once you have this one, now this can react this to give you the nitration product. On the other hand, if the nitration takes place, for example, in the para position, you will be able to have this resonance structure. If you look at here, it has the positive charge, it is less stable. When the nitration takes place para position, you have this problem. On the other hand, the reaction takes place meta position, you don't have this kind of intermediate. Therefore, whenever you have the electron donating group, the substitution reaction will take place ortho or para position. On the other hand, if you have the electron withdrawing group, the reaction will take place at the meta position. Now let us look at the next example, reaction of this alkene with this HCl. It can undergo, this is an electrophilic addition reaction, and you will be able to have a carbocation intermediate. Secondary carbocation which can react with Cl minus to give the addition product. On the other hand, this is secondary carbocation which can rearrange. Now this methyl group can migrate to give a tertiary carbocation. So this carbocation is more stable compared to secondary carbocation. Therefore, the methyl group migration can take place, and once you form this one, now the Cl minus can undergo reaction, then you will be able to form this chloro derivative. So in this reaction, you will have a mixture of compounds. If you look at the major product, this will be the major product, and first the alkene undergoes addition reaction with this proton to form a carbocation, secondary carbocation. The secondary carbocation now leads to the rearrangement. This methyl group moves from this carbon to here, and you will be able to form a tertiary carbocation. This then reacts with this Cl minus to give this chloro derivative. Now let us look at this example. So the reaction of this 1,3-diene, this HBr gives the addition product, and in this reaction, as just we have seen, can react with this proton to give a carbocation which can undergo reaction with Br minus. If you look at here, this sterically hindered, this tertiary carbocation, this is, then you can form this allyl carbocation. This is can exist in the equilibrium, which can undergo reaction to give this allyl bromide as the product. In this reaction, first it undergoes reaction with the proton to form the tertiary carbocation. This is the allyl carbocation which can exist equilibrium with this allyl carbocation. Once you form this one, this is sterically less hindered comparing to that. Therefore, the Br minus undergoes reaction here to give this allyl bromide as the product. This alkyne, when you react with hydrogen in the presence of palladium carbon catalyst, in the presence of quinoline, this is crucial here, it can undergo partial hydrogenation to give cis-2-butene as a product. On the other hand, when you react with sodium in liquid ammonia, and you will be able to form this trans-2-butene as the product. So when you look at the mechanism of this transformation, when you have the palladium on charcoal, which is absorbed with the hydrogen. Now let us look at the next example. This alkyne make chelation with the palladium, then the hydrogen adds the bottom phase to give this intermediate. Once you form this one, now it can undergo reaction here and you will be able to form the hydrogenation takes place the same phase of the alkyne. You get the cis alkene as the product. It doesn't undergo further reaction because due to the presence of quinoline, which can make chelation with your palladium, it can reduce the reactivity of palladium charcoal. Therefore, the reaction stops the alkene stage. It doesn't undergo further reaction to give alkane as a product. If we don't have the quinoline, it can further reduce the alkene into alkane as the product. So, using this method, you will be able to form the cis alkene as the product. In this case, you form 2-butene as the product. On the other hand, when you use sodium liquid ammonia, you will be able to form the trans alkene, trans 2-butene as the product. Formation of this can be explained as follows. When you have the alkyne, when you react with sodium, it can give one electron to alkyne and you will be able to form a radical anion. Once you form the radical anion, which can take proton from ammonia solvent, the basicity of this anion is higher comparing to this ammonia. Therefore, it can take proton from this solvent to form this vinyl radical. This radical can react with another sodium to form anion. Once you form this one, as just we have seen, it can take proton from the solvent to give trans alkene as the product. In this reaction, you generate 2 equivalent of sodamide as a byproduct. So, when you use sodium in liquid ammonia, you will be able to convert alkyne into trans alkene. On the other hand, when you use hydrogenation in the presence of quinoline, which is known as Lindlar catalyst. You can carry out partial hydrogenation to give alkene as the product. In this way, you will be able to form cis alkene as the product. Now, let us move to the hydration of alkene. When you react methyl cyclohexene with water in the presence of acid, you will be able to form the tertiary alcohol. It can undergo reaction with this proton source, you will be able to form the tertiary carbocation, which can react with water to produce the tertiary alcohol as the product. On the other hand, if you do hydroboration oxidation, you will get the other regioisomer, the formation of this alcohol can be explained as reaction of alkene with borane give the additional product. The reaction is stereospecific. The borane approaches from the less hindered side. The less substituted carbon syn addition takes place to give once we have this one, this can undergo reaction with hydrogen peroxide in the presence of base to give If you look at here, this hydrogen and hydroxy group comes to the same side, and the boron always approaches the less substituted carbon, and you can get the opposite regiochemistry when you see the acid base hydration, and in the case of hydroboration oxidation you get this alcohol as the product. Now let us look at the next example. Ozonolysis of this alkene in the presence of hydrogen peroxide. As we have seen, alkene can be converted into carbonyl compound by ozonolysis. In this reaction, this alkene will be oxidized into a mixture of carboxylic acid you will get mixture of this carboxylic acid. On the other hand, when you use hydrogen bromide in the presence of peroxide, it can undergo addition reaction via radical pathway. In the presence of peroxide, for example, when you use this peroxide, it can undergo homolytic cleavage. This can react with to the HBr to form Br radical. This radical can undergo addition reaction with this alkene to form a secondary radical. This radical now further can react with HBr, and in this way you will be able to form as the product. This regiochemistry is opposite to the electrophilic addition reaction, in that the bromine will add in this carbon. When you carry out the reaction via radical pathway, you will be able to form this primary alkyl bromide as the product. Ozonolysis already we have studied, and it can undergo addition reaction to form a ozonide. As intermediate, once you form this one, when you treat with hydrogen peroxide, in this case it can undergo oxidative cleavage to give a mixture of these two carboxylic acids. In place of peroxide, you can also use oxygen. It can also generate radical. Once you form the radical, it can undergo addition reaction shown here, and you will be able to get this alkyl bromide as the product. The next problem is, among the following compounds, the aromatic compounds is or are. If you look at the features that need to a compound to be aromatic, The compound should be cyclic. You should have a delocalized bielectrons. You should have four n plus 2 bielectrons, and it should be a planar. For a compound to be aromatic, it has to satisfy these 4 points. If you look at all these compounds are planar, cyclic. Now we have to look at whether they have the delocalized pi electrons as well as whether they have 4n plus 2 bielectrons. N can be 0, 1, 2, 3 and so on. Now let us look at here. This is a cyclopropenyl cation. It has 2 pi electrons. It has a delocalized pi electrons. So this is aromatic. Cyclopropenyl carbocation is the smallest aromatic compound. Now let us look at this one, cyclopentadienyl anion, which has 6 pi electrons. This also has a delocalized bielectrons, therefore this also aromatic. When you look at this compound, it has 6 pi electrons, however doesn't have the delocalized pi electrons since you have the here CH2. Therefore this compound is not aromatic. On the other hand, when you look at this one, the cycloheptatrienol carbocation, and this is also has 6 pi electrons. The pi electrons are delocalized, therefore this is aromatic. This has 10 pi electrons. It has the delocalized pi electron, therefore this is aromatic. The 4 compounds are aromatic and this compound is not aromatic because of it lacks the delocalization of the bielectrons. Now let us look at this problem. The major product of the reaction of 2-bromobutane with the sodium ethoxide is so when you react with sodium ethoxide, it can produce a mixture of alkene, say E2 elimination, on the other hand, if you deprotonate this hydrogen, and you will be able to form a mixture of 2-butene, and if you look at the ratio of these compounds, so this will be the major compound, and when you compare these two alkenes, this is the more substituted alkene. So this compound will be produced more because of the stability of this alkene comparing to this one. And now we have to look at here, you have the trans as well as cis alkene among this, and this will be the major compound. This can be explained through the Newman projection. If you draw the Newman projection of this 2-bromobutane, if you look at these two conformations, this is more favored, and because it is less sterically hindered and this maintains the anti-periplenarity, it can lead to the formation of the trans olefin. On the other hand, this can lead to the formation of cis olefin because of this, and this will be the formation of this trans olefin will be higher, and this reaction proceeds via E2 elimination. For E2 elimination, the anti-periplenarity of this hydrogen and PR is essential, and when it can easily undergo E2 elimination to give this alkene as the major product. In this, although a mixture of alkenes are produced, and this this E alkene will be the major product comparing to Z alkene. In summary, we have seen problems related to ozonolysis. We also have seen the use of haloform, tolerance and Felling's test, which are commonly used to find out the functional group. Haloform test, as just we have seen, is used to find out the presence of methyl group which is bonded to the carbonyl group. When we react with sodium hypohalite, it can be oxidized to carboxylic acid and haloform. Tolerance and Felling's test are used to find out the presence of aldehyde functional group. Tolerance reagent can be prepared from the silver nitrate, sodium hydroxide and ammonium hydroxide solution when you mix, and you will be able to form a silver complex which can oxidize aldehyde to carboxylic acid, where silver 1 will be reduced to silver 0. And similarly, Felling's solution which can be prepared from the copper sulfate and sodium potassium salt of tartaric acid, which can be used to find out the presence of aldehyde group. Aldehyde will be oxidized to carboxylic acid, where the copper 2 will be reduced to copper 1 oxide as red brown precipitate. We can easily find out the presence of aldehyde functional group using this tolerance and Felling's reagents. Then we have seen the aromaticity. For a compound to be aromatic, it should satisfy 4 aspects. It should be planar, should have delocalized pi electrons, should have a 4n plus 2 pi electrons, and should be cyclic. Then we have seen the chemoselective reduction of nitro group. If you have dinitrobenzene, you can try to selectively reduce one of the nitro group using sodium sulfide. We have seen an example. Then we have seen the aromatic electrophilic substitution. We have seen several reactions. For example, nitration of nitrobenzene. The nitration takes place at the meta position. Whenever you have the electron withdrawing group, the electrophilic substitution takes place at the meta position. On the other hand, if you have the electron donating group, the reaction usually takes place at the para and ortho positions. We have seen one example for the alkylation. If you have the isopropyl chloride, you can try to react with benzene in the presence of Lewis acid like aluminum chloride. We have seen the preparation of cumene, which can be oxidized to cumyl hydroperoxide using oxygen under heating. The cumyl hydroperoxide can be converted into phenol and acetone by treating with acid. This is an industrial process we use to prepare phenol. Similarly, if you have the alkyl halide, you can try to react with benzene via aromatic electrophilic substitution, which is known as Friedel-Crafts alkylation. Similarly, you can also try to, if you have the acid anhydride, acid chloride, you can carry out the acylation, which is known as Friedel-Crafts acylation. You can carry out this reaction using Lewis acid like aluminum chloride. Then we have seen the hydration of alkenes and alkynes. You can reverse the stereochemistry. If you carry out the reaction with water in the presence of acid, you will be able to form the more substituted alcohol as the product. On the other hand, if you use the hydroporation oxidation, you get the left substituted alcohol as the product. If you have the alkene, you can convert into alcohol using these approaches. Similarly, you can also, alkyne also can be reacted with water in the presence of acid to give enol, which will be converted into ketone, depends upon the nature of the alkyne. Similarly, you can also react with bulky borane to give the addition compound, which can be oxidized to hydrox group, can be converted into aldehyde or ketone, depends upon the nature of the substrate. Then we have seen the hydrogenation, partial hydrogenation of alkyne using palladium charcoal, which reduces alkyne into alkene in the presence of quinoline, which is known as Lindlar catalyst, which can be used for the partial hydrogenation of alkyne to alkene. You get the cis alkene as the product. You can also convert into trans alkene using sodium liquid ammonia. The reaction is stereospecific specific. Then we have seen an example for elimination reaction. You will end up with more substituted alkene as the product. Then we have seen an example for the radical reaction. If you have the peroxide, which can react with hydrogen halide to form a radical species, which can undergo addition reaction with alkene to give the alkyl halide as a product. I hope that this presentation will be useful to you. With this, we conclude this lecture. Thank you very much.